Okay. Okay. Hello, everyone. Welcome back. So before we begin, a quick note on the reading for this week. So if you go to the website, the course website, like you should see the reading for this week, which is this really useful must-read article by Pedro Domingos on a few useful things to learn, like to know about machine learning. So uh, the reason why I give this reading in the middle of the course is because now you know all the basic foundation, like you have all the basic foundations that you can actually make use of this like this article. So this is the reading for this week. And if you haven't finished the previous readings, like I would encourage you to finish them as well. Okay, so let us start. Um, Let me share my screen. Okay, so just to recap what we discussed in the previous lecture. So we started with perceptron, right? And we found that perceptron had two issues. The first issue is it doesn't have a unique solution, right? So it has no unique solution. So we wanted a unique solution, which is the optimal separating hyperplane between the two classes. And that is done and that resulted in the max margin classifier, right? And the second issue was both the perceptron and the max margin classifier cannot work with overlapping class distributions, right? Like, so when the data set is not linearly separable, these two algorithms are not going to work. So we wanted to handle overlapping class distributions, right? And that resulted in the final support vector machine algorithm, right? So I think by the end of the lecture, like I wanted to answer the question, like, so, which if I go back to the previous lecture, so what is the error function that the SVM classifier is trying to minimize, right? Like, so what is the error function that the soft max margin classifier or the SVM classifier is trying to minimize, right? So now to remind you of the hard version of the max margin classifier, right? The hard version, the error function was summation n is equal to 1 to capital N, E infinity of y of n, t of n, I think -1, right? Plus lambda times w square. Is that correct? Let's go back and check. Yeah. Okay. Where the E infinity function was given as 0 if z is greater than or equal to 0 and infinity otherwise, right? So this hard max margin classifier had a very hard constraint that every correct example has, like every example in the class has to lie within the margin, right? And what we did in the soft version or the SVM formulation that we had is to relax these constraints, right? Like, and we had like extra epsilon or slack variable to allow some constraint violations, right? Like, so just to remind you about the support vector machine again. So let's say this is my boundary, okay? And then you have this idea of margin in both the sides, right? So now any data point, let's take a data point, like any data point that lies within the margin, right? Let's this or this, right? So now these two data points, since they are lying within the margin, they're going to have epsilon is equal to 0. Okay, where epsilon is the slack variable, right? So now if anything is lying between my margin and the decision boundary. Let's take an example. This one. Now this is going to have epsilon lesser than 1, right? So up to epsilon is equal to 1 is fine because it will be correctly classified. But what happens if the example crosses the boundary? Like if I have an example, green example, which is supposed to be in this side of the boundary, it is in the other side. Now this is going to have epsilon greater than 1. Okay. Now for points on the correct side of the margin, if they are in the correct side of the margin, then y of n, t of n should be greater than or equal to 1, right? So then we have the epsilon equal to 0. Now for remaining points, okay, epsilon is non-zero. It is given by 1 minus y of n, t of n. Okay, so you don't have any slack if you're in the right side. If you're not in the right side, this is the amount of slack that you have. Okay, now using this, I can write an objective function for SVM. So the SVM objective function can be written as summation over n is equal to 1 to capital N, okay, E s, like let's just call it as ESV of y of n, t of n, okay, plus lambda times W square, okay, where lambda is actually 1 over 2c, where c is the cost parameter, okay. Now what is this ESV? ESV of y of n, t of n is defined as maximum of 0, comma 1 minus y of n, t of n. Okay, so now I can also write this as 1 minus y of n, t of n plus. So what does this mean? So whenever this error is greater than 0, then that is my error. If the example is in the correct side, if this value is less than 0, then it is not an error because the example is already in the correct side. So you would do a maximum of 0 comma error, so it becomes 0. Okay, or in other words, this support vector error function is 0 whenever the example is correct, and it is a linear function of the error whenever it is not correct. Okay, so now this specific error function has a name, so this is known as hinge loss. Okay, so now we are seeing a new error function, right? Like, so can someone tell me what are the different loss functions we have seen so far in this course? Maybe in the chat. Okay, so there is MSE. Okay, what else? There is 0-1 loss. Yes. What else? Yeah, we have done maximum likelihood estimation. But it's the loss that we use in maximum likelihood estimation. Let's just call that as logistic regression error. Okay, the cross entropy error. Okay. Is there anything else that we have seen so far? No. Okay, so now then there is hinge loss now. Okay, so now let's look at how all these different loss functions compare with each other. So here is the graph of all the loss functions we have seen so far. Okay, so the black step function that you see, right? So which is 1 whenever there is an error and 0 whenever there is no error, right? So now this step function is the 0-1 loss, or we could also call that as misclassification error. Okay, this is a step function. Okay, now can someone guess what is the green color loss? In the chat, maybe. So what is the green color loss? Okay, it's the squared error, right? Okay, a lot of you say this is a squared error. Why? Because it's like it's zero here, and it increases monotonically in both the sides, right? Like so. Now this is the squared error that we have seen. Okay. Now, which one of the two, blue or red, is the okay? Now don't type in chat. I'm going to do a poll. So I want you to recognize which one of the blue and red is the hinge loss. Okay. So which is the hinge loss? Okay. So we are going to do a template poll. Okay. So which one of the two is the hinge loss? Like you press A for blue and B for red. Okay. Let's start the poll. Okay, so which one of them is hinge loss, like blue or red? Okay, I will be stopping the poll soon. Okay, let's stop. Okay, so I see 80% of you have answered it is blue. That's right, right? Like so, because if you look at the blue, you see that it's actually zero starting from one. So whenever it is correctly classified, the error is zero, right? So this part is zero. And for the rest of the part, like where you make an error, then it has a linear error, right? So the blue line is the hinge loss. Okay, and the one that is left out, the red one, is the logistic regression error. Okay, now if you remember our discussion on logistic regression, we were using, okay, a quick note. In the case of logistic regression, we were using the target variables to be 0 and 1, right? On the other hand, in the case of SVM, we are using the target values to be -1, 1, right? So now how did I make, like how do I compare them together, right? Like so for comparison, like all I have done in this graph is I first reformulated the maximum likelihood logistic regression using t belonging to -1 and 1. Okay, so how do we do that? So the probability that t is equal to 1 given y is given by sigma of y. So this is logistic regression, right? Now, for the probability that t is equal to -1 given y is given by 1 minus sigma of y, right? That was the probability for t is equal to 0 before. Now, by property of sigmoid function that we have seen before, this is sigma of minus y. Okay, now I can actually combine this and this together and just write the probability of t given y is equal to sigma of yt. So if it is positive, it's going to be sigma of y. If it is negative, it's going to be minus sigma of y. Okay, so now I can do my loss. The negative log likelihood is given by minus ln p of d, right? It's basically minus ln product over n is equal to 1 to n sigma of t of n y of n. Okay, so let me move this to the next page. Okay, now this is basically minus summation over n is equal to 1 to capital N ln. I'm going to expand sigma, so it becomes 1 by 1 plus e power minus t of n y of n, or in other words, summation over n is equal to 1 to capital N ln 1 plus x of minus t of n y of n. I just bring in the minus. Okay, now I can add an L2 regularizer to this. The loss function becomes summation over n is equal to 1 to capital N ELR of y of n t of n plus lambda times. So I'm doing all this reformulation just to have an equivalent loss function like how we had for say the hinge loss. Okay, so here ELR is given by this. Okay, and you just divide the whole thing by ln 2 so that the error function actually passes through 0, 1. Okay, so this is just a reformulation of the logistic regression error that we have already seen, and you see the effect here. So because of this reformulation, the error actually passes through 0, 1. Okay, and you can see that the logistic regression and hinge loss are almost similar, except for the fact that hinge loss is a bit flat, right? So now that has some like effect on the kind of solutions that we are going to learn. Okay, so now given that we have actually seen a bunch of loss functions, like I would like to take a quick detour and talk about loss functions. Okay, so remember that, okay, so what is the loss function that we actually want to minimize in classification out of these different loss functions? So what are the loss functions we have seen so far? So we have seen squared error. We started with squared error, right? So we have seen squared error. So we have seen 0, 1 loss. We have seen logistic regression loss. And we have seen hinge loss, right? Why do we have so many loss function? So which loss function is better, like, or what do we care about? So probably it's better if someone raise hand and tell me the answer. Any answer? Someone wants to tell me which loss function do we really care about, and like why do we have so many loss functions? Hand raise, please. So I would like to hear an answer. At least which of these loss functions is the most important one, or like what do we really want to minimize in our prediction system? Okay, I would be disappointed if no one answers. Okay, someone says logistic. Why logistic? Okay, so why is logistic regression loss important? Like, so any other answers? Okay, it's simple and fast. Okay, someone says hinge. Okay, maybe I should have had a bigger poll to know like which loss function people think is important. Okay, any other answers? Okay, we want to minimize the misclassifications. Okay, so which loss function corresponds to misclassification? So there is an answer which is depends on the problem. Does it really depend on the problem? Like, so what is your end goal? Like, if you want to come up with a classifier, like what is the loss that you want the classifier to minimize? Like, what is the loss that you want the classifier to have 0 value on? Okay, someone says it depends on the algorithm. So let's forget about algorithm. Okay, so let's just think about this from the user perspective. I don't know what is the algorithm. It's a black box. Okay, you could come up with any algorithm that you want. I don't care. So as an user of a system, like which is the loss that I would like to go see, like to go 0. Okay, Gabriel. Finally, someone is raising hand. Sharon, can you unmute?
Well, the end goal is to maximize the accuracy. So you want to minimize the 0, 1 loss, but
Yes.
it's hard to, but you cannot do it directly. You have to go through other loss functions like cross entropy, because you can compute the gradient. That's my answer. Or
okay, yeah, okay, that's a perfect answer. So remember that our end goal is just accuracy, right? Like, so, okay, thank you, Gabriel. Okay, so remember that our end goal is accuracy, right? Like, so we want a system which has 0 misclassification, right? So our goal is to have a system which has minimum misclassification error. Okay. And the problem with the 0, 1 error, as we discussed before during the perceptron lecture, is it's not continuous. And its gradient is 0 almost everywhere, right? So in general, it's very hard to minimize this error function. So what different algorithms are trying to do is to come up with a proxy loss for 0, 1 loss function. Okay. Now, in the case of logistic regression, the proxy loss is logistic regression loss. Okay. In the case of SVMs, the proxy loss is hinge loss. In the case of indicator regression classifiers, the proxy loss is squared error. Right? Now, all these loss functions, if you look at them, they are just continuous approximation of the misclassification error, right? But there is a problem with squared error. Okay, can someone tell me what is the problem with squared error by looking at this figure? Well, it takes forever to get a hand raise, so maybe you could also type it in the chat. So what's the issue with squared loss? I claim that it's not a good loss for classification. So why is it? Yeah, so as someone points out in the chat, so it has high error on correctly classified examples as well, right? Like, so you see that the error is 0 only when the value is exactly 1. When the value is like, for examples which are overconfidently correctly classified, right? Like, so the error just goes up, right? So squared error is a bad choice, okay, simply because it penalizes even in the correct side, right? So penalizes even in correct side, right? Like, so what we need is some loss which is monotonically decreasing. Okay, so now if you go back to this picture again, you could see both the red color line and, like, well, except for the square loss, everything else is monotonically decreasing, right? So ideally we prefer a logistic regression loss or an SVM loss. Okay, so even between logistic error versus hinge loss, right? So even between these two things, you could see that they look almost very similar, except for the fact that hinge loss is flat, and hence this would lead to sparse solutions. Okay. Okay. So, okay, now that was a bit like little bit, I think, very useful detour on loss functions. So we will see some other new loss functions too in the course. At that point, we will come back to this figure again and try to discuss the advantages and disadvantages. Okay. Okay. Now I would like to introduce, okay, so there is a hand raise, Krunal.
Can you explain again why the solutions would be sparse?
It's because it is okay. So in the case of hinge loss, like, it is the flatness of the loss leads to sparse solutions. But you could also bring that with your logistic error by just adding an L1 regularization.
Okay.
Okay. Okay. So now at this point, like, I would also like to introduce like so far we have seen 3 categories of classification models, right? Like, so generative models, discriminative models, and discriminant based models. So at this point, like, I would like to bring introduce another, like, different categorization of all these classification methods, okay, which is the idea of parametric methods versus non-parametric methods. Okay, now let's go back to our SVM's formulations. Okay, so in the case of SVM, we had two formulations, the primal formulation and the dual formulation, right? In the case of primal formulation, we had a bunch of W and we were learning those W. And once you have the W, you throw away all the data and just use W to make predictions, right? On the other hand, the dual formulation was slightly different than the tradition, like the usual classifiers that we have seen so far, right? Like, so in the case of dual formulation, we had a bunch of Lagrange multipliers, right? Okay, I don't remember the variable that we used for Lagrange multipliers. Was it lambda or A? A. Okay, so we had a bunch of Lagrange multipliers A, right? And in the case of the dual formulation, after learning these A, we cannot throw away all the data out, right? Because along with the A, there were also other parameters of the models, which were basically the support vectors, right? So you need to store those examples, which are support vectors, to make the decision in the dual SVM classifier, right? Now, this is slightly different from the primal version, right? Like, so in the case of primal version, if you have 100 parameters, then you just have 100 parameters. It doesn't matter how many examples you have in the data set. But in the case of dual formulation, now the number of support vectors could vary based on the complexity of the task, right? For simple tasks, maybe there are only 3 support vectors. For complex tasks, maybe there are 100 support vectors or 1,000 support vectors, right? Like, so now this contrast in these algorithms can be captured by the idea of parametric versus non-parametric methods, okay? So what are parametric methods? Parametric methods have a finite, fixed number of parameters, okay? On the other hand, non-parametric methods can, in theory, have infinite number of parameters, okay? The word non-parametric method is a bit confusing because you might think that when I say non-parametric, it means no parameters. It actually means there are infinite number of parameters, okay? Now, the number of parameters in parametric method is actually independent of data set, okay? On the other hand, the number of parameters in this parametric method is, so non-parametric method is dependent on the data set. Okay, now to give you some example for parametric methods, so we have seen logistic regression, right? In the case of logistic regression, you have a bunch of parameters, you're learning those parameters. Once you learn the parameter, you throw away the data, right? Similarly, GDA, you have a bunch of parameters, right? Primal SVM, right? Okay. Now, in the case of non-parametric methods, dual SVM is an example where you actually store the support vectors. We have also seen another non-parametric method in this course. So can someone tell me what is the other algorithm, which is also non-parametric? Okay, a lot of you answer. Well, like it's good. I would be more happy if this is even without reading the lecture notes, but even if you have read the lecture notes, that is also good. So I'm happy either ways. Okay, so K-nearest neighbor. Right? So what do we do in K-nearest neighbor? In the case of K-nearest neighbor, you store all the examples, right? Like it's actually dumber version than SVM, right? Like in the case of SVM, you're being clever and you're just storing the support vectors. But in the case of K-nearest neighbor, you store all the examples. Now, as the data set size grows, the parameters in K-nearest neighbor is actually the examples themselves, right? So as the data set grows, the number of parameters also grows. Okay. Okay. So now let me quickly talk about these two non-parametric methods that we have seen so far. The first one is the dual view of SVM. Okay. So in this case, we need to store the support vectors. Okay. and the number of support vectors is dependent on the dataset complexity. If you have more complex dataset, probably there will be more support vectors, okay? And on the other hand, K-nearest neighbor is even worse because it needs to store all the training points, okay? So KNN is something that we did not spend a lot of time in this course, right? Like unlike other algorithms, right? Like, so maybe it is worth mentioning a quick side note about KNN classifier. So you could call KNN as a lazy classifier actually. So why? Because if you think about K-nearest, like after learning all these algorithms, if you go back to K-nearest neighbor, so what was learning in K-nearest neighbor, right? Like, so there is no learning in K-nearest neighbor. Instead, you are just storing every example in the memory, right? And most of the computation actually happens during the prediction stage, right? So it's lazy, but the laziness has a cost. So since you're lazy while learning, you have to spend a lot of time during prediction. Like you have to go through the examples, find the nearest neighbors, and make a prediction based on that, right? So you have to do a lot of work during the prediction. On the other hand, in the case of parametric methods, it could be like million data points, it could be like 100,000 data points, it could be 1,000 data points. Like once you learn the parameters, then that's it. You throw away the data. Now inference is very fast, right? So, okay, any questions about whatever we have seen so far?
Sure, there are a couple of questions in the chat. So one question is that what is a parameter in KNN that is infinite?
Well, I think I answered it, right? Like, so in the case of K-nearest neighbor, the examples are the parameters because you're storing all the examples.
Yeah, and there's one more question, like regarding the sparse solution you have mentioned for hinge loss. What does sparse exactly mean here?
Oh, sparse just means that like most of the features go to zero, right? Like, so if you have 100,000 features, like if you, for example, like L1 regularization leads to sparse solution, right? Like, so what does that mean? Like, so a lot of like uninteresting or irrelevant features goes to zero, so that while doing inference, you have lesser computation.
That's it.
Okay. So I also want to do another quick reminder about what we have learned like previously, which is the idea of basis function. Okay, so we have seen a lot of linear models, right? Like, so now I would like to remind the power of basis functions again. Okay, so the power of basis functions is in such a way that you could actually take any linear model that we have learned so far. Okay, so any linear model that we have learned so far in this course, or even generalized linear models, which are super class, right? Like, so you could take all these things, okay, and you could just add nonlinear basis functions, okay, and you get nonlinear decision boundary. Okay, so now as we progress, like we are going to see truly nonlinear models. But so far we have spent a lot of time on linear models, and it is not a waste of time. One, they are foundations. Two, you can actually make all these models learn nonlinear decision boundary by just adding nonlinear basis functions. Okay, so just to give you an example, like, so here is a logistic regression classifier. Okay, so what I have done here is I have taken this data, which seems to be non-linearly separable, right? Like, so you need a circle to separate the blue and red, right? I converted the data into phi1 and phi2. Okay, so phi1 and phi2 are some Gaussian basis functions. They are centered around this plus symbols. Okay, now once I convert in this converted space, you see that it's linearly separable. So I draw a line. Okay. So now this line, right? So the line in phi space, if you actually project it to the original space, project to x1, x2, okay, it is actually a circle. Okay, so now you learn a linear model on the top of a nonlinear basis function. Now you project it back to the original x, you get a nonlinear decision boundary, right? Even though this says that basis functions are very powerful, but there is just a quick warning, right? So constructing basis functions, right, is not easy. It's not very easy, or like it's not like a one-time job like that. Then you could use it for every data, right? Like, so you have to construct the basis functions carefully for every data and for every task, which could be time-consuming or tedious or painful, right? So what we will see in the future lectures is to we are going to talk about algorithms which are like nonlinear, like the models which are nonlinear by itself, that you can directly learn the nonlinear decision boundaries. Okay, so I think this concludes our discussion on like discriminant based models. Like, we had a lot of detour in the end, just to remind ourselves on things that we have learned previously. Okay, so now we are going to slightly switch gears and look at a totally different type of classification algorithm, okay, which is going to be very different from things that we have already seen so far in the course. Okay, so now we are going to look at what is known as decision trees. Okay, so what is decision tree? So this is a classifier which is tree structure, as the name suggests, right? Like, and you're going to have a bunch of decisions that you will be taking along the tree, and the leaves of the tree is going to tell you what is the class. Okay, now this is very different from other models that we have seen so far, where you just have a matrix multiplication, and in the end, you have a value which is a prediction, right? Okay, so now let's look at an example. So here is an example. Like, so in the left side, you see the training data, right? So now this is, I think, a bank loan defaulting problem. Like, so given a bunch of features about a particular application, right? Like, so does he own a home? What is his marital status? And like, what's the annual income? So given these bunch of values, now I want to predict whether this particular loan applicant will default or not, whether he's going to default and like not pay the loan or not. Okay, now in the right side, you actually have a decision tree. Now, what does this decision tree say? So this decision tree tells that you should first start with checking the attribute homeowner. Okay, so the decision tree tells you that if someone is a owner of the house, if it is yes, you go this way, right? Then it says he will not default, which is a reasonable rule, right? Like, so now these are kind of heuristics or rules, whatever you want to call it, right? Like, so now this path tells you that if the applicant has a home, then he will not default, so you can give loan to him. Okay, if he doesn't have a home, then the decision tree asks you to go to the right side. Now you check the marital status. Okay, so for some reason, this decision tree thinks that if the person is married, he will not default, so he will pay the loan properly. Okay, so answer is no. If he's not married, like if he's single or divorced, then you check the income. Okay, now if the income is less than 80K, this is a weird rule. It says that if the income is less, he will not default. If the income is more, he defaults. Okay, so it's a weird rule, but this is one example classifier decision tree. Okay, now how do I, okay, so there are, first question, how do I jump from here to here, right? Like, so how to construct the decision tree. Any idea? I think it's easier if someone can raise your hand and answer. So given a data set like this, I want you to come up with a decision tree. Okay. How would you go about constructing such a tree? Any answer? Jackie?
Hi.
Yeah.
Yeah. I don't. Maybe random forest. Random decision.
Sorry.
Maybe random forest or something like that.
No. Well, like probably that is not what I'm looking for. There are two other hand raisers. Maybe someone else wants to try.
If it is like 100% possible to do it, then maybe you can write this data as Boolean variables and things like that, and then just resolve those clauses, and that will give you a full rule set that is minimal. That you can just split it into a tree.
Okay, can you repeat, please?
So this is basically like a Boolean clause, right? So for example, the first one is value yes is true, marital status, let's just say single and divorced, single and married. So this is also true. And income is let's just say some value like greater than 80 or less than 80, and that is also true. And then the answer is no. Like that way, you have a full Boolean table,
Yeah.
and then you can resolve clauses to learn like the complete tree.
Okay, so I think, okay, let me rephrase your suggestion. So Krunal's suggestion is like you could consider the tree as every path in the tree as some sort of Boolean function in the features. So you construct the Boolean table and then find
Yeah, and
things
then
like
you just resolve the clauses like
okay.
if something is true, basically regular satisfiability clause resolution processes.
Okay.
Like if P and not P is there, then you just merge them and things like that.
Okay. So any other suggestions?
There are a couple of answers in the chat, Sarath. Conditional probability.
Okay, what is conditional probability?
There's one more answer. Choose a feature with high Gini.
No, don't tell that answer. Okay, so when I ask the question, like I want you to answer based on your intuition, not based on the notes.
I think by conditional probability, he meant one feature dependent on how it is depending on the previous feature, something like that.
Okay, so okay, a lot of you are answering by most of the answers tells me that you have already read the notes, but it would be interesting if someone who hasn't read the notes can try to come up with an algorithm. So Krunal gave an answer. So is there any other? Okay, so well, Gary, then probably you already have seen decision trees. Okay, so is there any other solution? Yomna?
Yeah, I would go with, because at each node is going to split the data in two groups, and then every group is going to be split again in two groups. So I would start by looking at the output and try to find an attribute that splits the data as quickly as possible in two groups that are uniform, and then restart with every subgroup.
Okay, what do you mean by uniform?
Uniform meaning all yeses, all no's.
Okay, so that's
And
not uniform. So when what I meant, what I thought as uniform is like when you say uniform, it could be 50% yes, 50% no. So by uniform, you mean like try to divide it into two groups such that it is either all yes or all no, right?
exactly, that are heterogeneous, actually.
Okay.
So
Okay. Yeah. So I think okay, this is also a good general idea, right? Like so what our Krunal suggested is also valid, but that is computationally very expensive to do, right? Like on the other hand, what Yomna suggested is a slightly I'm not sure how clever, but like more clever than like going through all the classes, right? Like so what about the second suggestion that we have now? So we're going to expand on that. Okay, so how to learn a decision tree. By the way, there are like many ways of learning the decision tree, but we would just see one flavor of the algorithm. And if you want to explore a lot, like more about decision trees, like you could go read by yourselves. Okay, so how to learn the decision tree from the given data set. Okay, so what we are going to do is, as Yomna suggested, we will look for the feature. Okay, I'm going to call that as more discriminative. Okay, a feature which is going to tell me correctly identify something is yes or no. Okay, so like for example, if I have a feature which, okay, let's take homeowner for example, right? So you look at this data set. Whenever homeowner is yes, right? So you see that there are three examples of homeowner being yes, and in all the three examples, the defaulted borrower is no, right? Then it is a very clear indicator that whenever someone owns a house, they are not going to default, right? So we will look for such indicative features. Okay, now this algorithm, like a simple version of this algorithm, is proposed by Hunt. So it's called Hunt's algorithm. Okay, so now let DT be the set of all training examples that reach a node T. Okay, I am at a node. Let's say initially I'm in the root node. I have DT, which is a set of all the examples. Okay, now how do I divide it, or how do I find the right attribute? Okay, so here is a general procedure. We are going to expand on this procedure in the next lecture. Okay, so but I'll just give you a rough idea of the solution. So the rough idea is, if DT contains examples that belong to same class, okay, YT. If I have a data set where all the examples belong to class YT, okay, then you will just stop the process here. Then T is a leaf node labeled, you will label it as YT. Okay, similarly, if DT is an empty set, okay, so I'm giving you a recursive algorithm here. So you have an empty set, like you start with the data, you divide it, and you reach a node where it is an empty set. Okay, then T is a leaf node labeled by some default class. Let's call it YD. Okay, now what is more interesting case is if DT contains records or examples from both classes or more than, we don't know how many classes, right? Like, so from more than one class. Okay, so then we are going to use an attribute test to split the data into smaller sets. Okay, so what is the most non-trivial part of this algorithm is how am I going to do this split? Okay, but once I do the split, then I'm going to recursively apply this procedure to each subset. Okay, so what am I doing here? So I take the data. Okay, my iPad is not moving. Okay, so what am I doing here? So I take the data okay, and find a right attribute to split the data. So once I split it, the hope is that the new data sets that I have received are going to be more more discriminative, or like there's more chance that like something is all yes, something is all no. Okay. Now, if it is not the case, then you further split. You continue the splitting process until either you reach a node where all the examples are yes or all the examples are no, and then you stop, or reach a situation where you have tried all the attributes. Now you have empty data set, in which case you stop with a default classifier. Okay. Now, I think in the next lecture, we would talk about how to come up with these tests, right? Like, so different people gave different answers in chat. We will actually look at those process, like procedures in detail. Okay, so I think I will stop here. I'll take probably 1 or 2 questions before I stop the recording. Many questions? Always a problem covered by one tree. Well, okay. We have started with this problem, which is the idea of, given a data set, how can I come up with one tree? But I guess what you mean by the question is like random forest and other algorithms where you have multiple trees, right? Like, so we would cover them probably in the next week. How to determine the root node is exactly what we will answer as a first thing in the next lecture. So maybe it's a thinking exercise for you. So think about how to determine the root node without looking at the lecture notes.
But yeah, Sharad, we can always cover a problem with one tree, right? I mean, we don't need.
Yes. Yes. Okay, any other question? Decision tree is just for classification. That is a good question. So maybe I would ask the same question to you guys. So can I use decision tree for regression? Okay, so some of you say yes. I will let you guys. Okay, so whoever asked, can we use decision tree for anything other than classification? Can you ask the same question in the end of the next lecture? I don't want to give the answer now. I'll just give some time for people to think. So I want you guys to think about how to use decision trees for regression. Okay, so ask me the same question in the end of the next lecture. I'm going to answer that. But till then, like, I want you to think about how to use decision trees for regression. The answer is yes, you can use it. Come up with an algorithm. Okay, maybe I'll stop the recording here.